Chapter 7, Chemical Reactions. So what are some ways that we can observe that a chemical reaction has actually taken place? So the first thing is if a solid is formed. Another thing that we can form in a reaction is a gas. Another way to tell a reaction has occurred is if there is a heat change involved, which means exothermic, the solution gets warm, or endothermic, the solution gets cold. Oftentimes, a color change can indicate that a reaction. The only exception to this would be if you're doing a dilution in which the color would remain the same color, right? So it's just looking less bright. And then the last way to show a reaction has occurred is that it gives off light. In looking at a chemical equation, which is just our way with symbols to represent a chemical reaction, what is the information that this equation tells us about a particular reaction? Well, we can look here, and in the parentheses, we have S for solid, L for liquid, G for gas, and sometimes you'll also see AQ, which means that it's an aqueous solution. Your reactants are always shown on the left side of the arrow. Your products are always shown on the right side of the arrow. We also see coefficients sometimes in a balanced equation. Well, they have to be if it's a balanced equation. And this just basically tells us how many of a particular compound is going to react, and then how many different products might we get out of it. And when we have balanced the equation, we are obeying the law of conservation of mass. Sometimes there's a little triangle written above the arrow, and that just shows that there was heat involved, or heat was needed. So the 5 different things are: we indicate states of matter, we have reactants on the left, products on the right, we're expressing the amount of substances, which is basically like a chemical recipe, and that sometimes we indicate that heat is involved. So when we're looking at a chemical equation, it's showing us the quantity of reactants and the quantity of products that we're going to get out. We have to balance the equation by placing whole number coefficients before each formula. And those coefficients are looking at multiplying through however many respective atoms we have for a given compound. You're not allowed to balance an equation by changing the subscripts. If you change the subscript on a compound, then you are changing the identity of the compound, and that is not allowed. And the whole reason why we have to balance an equation is because the law of conservation of mass must be obeyed, which means that however much we start with has to be the same amount that we end with. In a chemical reaction, we're changing who we're bonded with. Bonds are broken and new bonds are being made. However, the number and type of atoms that you start with have to be the same number and type of atoms that you end with. So how do we go about balancing a chemical equation? First thing you have to do is make sure that you have the correct formulas and that we're putting the reactants on the left and the products on the right. So, for example, ethane reacts with oxygen to form carbon dioxide and water. Ethane is a type of hydrocarbon, so I wouldn't expect you guys to know that. I'd give you that formula. However, we should know what oxygen, carbon dioxide, and water are. So, C2H6 is ethane, oxygen is O2, remember it's a diatomic, CO2, carbon dioxide, and H2O for water. Clearly, in looking at this equation, we see that we do not have a balanced equation because I'm starting with 2 carbons, I only have 1. I have 6 hydrogens, I only have 2. I have 2 oxygens, and I have a total of 3 oxygens on this side. So we're going to look at how are we going to place certain coefficients so that we can have the same number of atoms on the left as we do on the right. And once again, we are not allowed to change the subscripts in a compound. So even though I need 2 carbons over here, I can't go and start changing and multiplying through and changing my subscripts. That's just not allowed, so don't even go. Also, never put coefficients in the middle of a compound. Your coefficient is always written directly to the left of whatever substance it is that you're balancing. So you can really start anywhere, but in a combustion reaction like this, you're going to want to start with carbon. And that's simply because over here, oxygen shows up in more than one place. So we just simply leave that for last. In other reactions, you can start with whatever. I'm just going to kind of hop back and forth across the arrow. And what you do to one side, you look, okay, well, how does it change something on the other side? And then you look back and you just keep doing that until all of your atoms are equal. So if we start with carbon, we see we have 2 on the left and only 1 on the right. This means that I have to multiply the CO2 by 2. So I place the 2 in front of the carbon dioxide. Now I have 6 hydrogens on the left, only 2 hydrogens on the right. So we're always asking ourselves, what number do I multiply by so that I have the same number of atoms? Well, 6 divided by 2 is 3, so I'm going to multiply water by 3. So at this point, I have my carbons and my hydrogens balanced. Continuing on, I now will balance my oxygen since it appears in more than one place. So I'm looking at what are the total number of oxygens I have on this. I have 2 times 2 from carbon dioxide, and then I have 3 times 1 for water. On the left, I have 2 oxygens in my diatomic molecule. So 2 clearly does not equal 7. So what I have to do then is multiply the oxygen by 7 halves. Right? It's a fraction, so 7 halves times 2 just equals 7. Now, because we can't have half of a molecule, we have to make sure that we have whole numbers by multiplying everything through by 2. So what you do to one side, you have to do to the other. And now we have 2C2H6 plus 7O2 yields 4CO2 plus 6H2O. The last thing that you're going to do is just check to make sure that you truly have balanced everything by going back and doing your atom count again. So we start with carbon. 4 carbons on the left, 4 carbons on the right. Hydrogen. I have 2 times 6, which is 12 hydrogens. I have 6 times 2, which is 12 hydrogens. And oxygen, I have 7 times 2 on my reactant side, and then I have 4 times 2, which is 8 from the carbon dioxide, plus 6 times 1, which comes from the water. And 8 plus 6 is 14. So we do have a balanced equation. We have observed the law of conservation of mass, and now we're done. So I'm looking at a visual representation of making sure that we are obeying the law of conservation of mass. If we react calcium hydroxide with hydrochloric acid, we produce calcium chloride and water. The water molecules aren't shown because they're just floating around. Hydrochloric acid is an aqueous solution, which means water is readily available. Without balancing this equation, we would not end up with our total number of reactants equaling our total number of products. So here we have our molecular weights, our formula masses, same thing. Once we have balanced the equation, we see that we actually have to have 2 of these to react with every one of these. That allows us to get our 74 plus 73 to add to 147. On the right side, our products, if we only had 1 water, clearly 111 plus 18 would not equal 147. So we show that we have to have 2 moles of this that are going to be produced. And then we have our total mass on the product equaling our total mass on the reactant side. So in the last chapter, we looked at making sure that we wrote balanced formulas, right? We had a correct compound for what was reacting. So if we start with hydrochloric acid and react it with calcium, we get calcium chloride and hydrogen as a gas. This is incorrect because calcium is a +2 charge, Cl is a -1. If we do our crisscross, we know that calcium chloride is really CaCl2. Hydrogen we know is a diatomic element, which means it never shows up without its buddy, another hydrogen atom. So down here, we have clearly identified the correct products. However, we have changed our subscripts to balance what we have over here. And this is saying we have an H2Cl2. That's not how hydrochloric acid looks. This is a completely different compound. So instead what we did, we actually have two individual hydrochloric acid molecules reacting with calcium to produce calcium chloride and hydrogen gas. We can see then that we have two H's, two Cl's, two Cl's, one Ca, and one Ca. So our balanced equation would then read 2HCl plus Ca yields CaCl2 plus H2. So what are some properties of solutions? Because most of what we're going to look at in the rest of this chapter has to deal with different types. So a solution is simply a homogeneous mixture, which means that it is the same consistency throughout. The two parts that make up a solution are your solute, which is the substance that's being dissolved, and it's typically in the smaller amount, and the solvent, which is the substance that is doing the dissolving. So the solvent is the dissolver. And for what we're studying, it's typically going to be water. So the solute goes into the solvent to make a solution. When your solvent is water, then we say that we have an aqueous solution. Now, solutions can be liquid, solids, or gases. An example of a solid solution would be an alloy. An example of a solution of gases would be the air that we breathe. So some other properties of solutions are they are clear, which is different than being cloudy. They're transparent, which means that we can see through them. And there's no visible particles floating around. Now, some solutions may have a color, but they still have to be clear and transparent. We've seen that different types of transition metal salts have specific colors associated with them. Therefore, when you dissolve them in water, the solution would take on the color of the water. Now, if something is going to be soluble in something else, that means that it will dissolve. There are rules in the book and that we will discuss that says whether or not a compound is going to be soluble in water. Things that are always soluble will be your group 1 metal cations. And for anions, we'd be looking at nitrate, acetate, and perchlorate as things that no matter who they're bonded with, they will always be soluble. If we're going to have a reaction in an aqueous solution, it means that we have to have ions floating around. So we say that they form electrolytes, which means basically that a solution where you can dissolve salts will conduct electricity. So we often hear about replenishing your electrolytes, drink some Gatorade, right? And it just has salt in it, sodium chloride, magnesium chloride, because when we sweat out salt. So we want to replenish that by drinking an electrolyte solution. If something is soluble and we put it in water, it's going to have an AQ next to it, meaning that it is aqueous solution. This is dissolved in it. You cannot see it. If it's not soluble, then it stays as a solid. So the type of reaction that we're going to look at in terms of forming a solid is what we call precipitation. And a precipitation reaction simply says that we're going to mix two aqueous solutions together and we're going to form a solid. So two clear solutions become cloudy, and then the cloudiness, those solid particles that are formed, are going to settle to the bottom, which is precipitation. When we talk about the weather, it's going to precipitate outside. We're either talking about rain or snow, and sometimes ice. So if we take sodium iodide and mix it with lead nitrate, what happens is the lead and the iodine are so attracted to each other that they're going to form a solid and fall out of solution together. So here's a balanced chemical equation showing that reaction in the previous slide. This is called a double displacement reaction because each partner has swapped. So the metal that is here is now with the nonmetal over here. The metal that's here is now with the group of nonmetals over here. So it's a double displacement or double replacement. Now, how would we know which of these we would identify as a solid and which would be aqueous? You simply just have to look at your solubility rules and say, oh, well, I know that sodium is always going to be aqueous, so I put an AQ next to it. I look and I see that oftentimes halogens are soluble unless they're with lead, mercury, or silver. So the S stands for solid. The S does not stand for soluble. This is our precipitate. It is the solid that is formed. So this is what we call our molecular equation. Now, if we want to look at what we call an ionic equation, what we do is we break apart everything that has an AQ next to it, and we give it its appropriate charge, keeping in mind that this would not exist as NO3 parentheses 2, right? The 2 is here to balance out the fact that lead is a 2 plus, nitrate is a -1. So when we break things apart, oftentimes our subscripts become our coefficients, right? But we cannot change nitrate because nitrate is what it is. So I'm not trying to separate this into nitrogen and oxygen. That would be incorrect. So we disassociate all of our aqueous substances, giving them their appropriate charges, and keeping in mind that we still have to have a balanced equation. If a reaction is going to occur, that means everything on the reactant side has to break apart, which we've shown down here. The thing that is solid does not break apart, but we once again have another aqueous component which does dissociate. From an ionic equation, we can go to a net ionic equation. And we do that by canceling out like things on the reactant side to the product side. In doing so, then, we get to the net ion, which says, I'm going to pull out the spectator ions, right? So spectators are something, go to a football game, you're a spectator. You're there, but you're not playing. In this instance, we can just think that sodium escorted iodine, the nitrate escorted lead to the game, and then they just stood back and watched the players play. So in a net ionic equation, your product will always be your precipitate, which means it always has to be the solid, never the aqueous substance. So in writing net ionic equations, we always have to start with a balanced molecular equation. We always break apart the things that are the electrolytes, which means they're aqueous. We cancel the spectator ions because they're not participating in the reaction. They're just hanging out. And then we make sure that our charges and number of atoms are always balanced when we get to the net ionic equation. If we were to write an equation and we didn't have charges, then it no longer is ionic. To be an ion, it means that you have to have a positive or a negative charge. So if we look at this reaction, silver nitrate reacts with sodium chloride to produce silver chloride and sodium nitrate. Well, since this is our precipitate, we know then that the ions that have to go into making it for a net ionic equation have to be Ag plus and Cl minus. So we'd write Ag plus aqueous plus Cl minus aqueous yields AgCl as a solid. And once again, our spectator ions are Na plus and NO3 minus. Here's just some other examples of precipitates that form when you mix different solutions together. So cadmium sulfide, lead 2 sulfide, nickel 2 hydroxide, and aluminum hydroxide. So what you have to do to form these is take two solutions that are aqueous, but then when you bring them together, they're going to form a solid. If you have two solids already in solution, they are not going to break apart and form a new solid because they're already stuck to something else. So another type of reaction we're going to study in this chapter deal with acids and bases. Some typical properties of acids are that they taste sour, which is why most citrus fruits, lemons and limes and grapefruit, all have a very tart taste that comes from the citric acid in them. Some acids have the capability of dissolving metals and sometimes producing hydrogen as a gas. And acids are typically going to form H plus in solution. And we just call an H plus a proton. Why is it called a proton? Because hydrogen starts with only one electron. So if it loses the electron, getting a positive charge, all that remains is a proton. Contrarily, bases tend to taste bitter. They're slippery, like soap. So bases are often found in soap. and they're going to form the hydroxide ion in solution. Some strong acids and bases that we typically will identify are your hydrochloric acid, hydrobromic, hydroiodic, nitric acid, sulfuric acid, and perchloric acid. Our strong bases are going to be all of your group 1 metal hydroxides, and then there are a few group 2 metal hydroxides that are also considered strong bases. So we can see that with our acids, right, they're all donating an H to the solution. And with our strong bases, they're all donating OHs, OH minuses to a solution. So if you're going to be a strong base, you have to be soluble. So some metal hydroxides, like we saw on the previous slide, or nickel 2 hydroxide, are not going to be strong bases because they stay stuck together. So the reactions that we typical one would be a neutralization reaction. So what we have is, well, these are not shifted to the right place, but our acid is HCl. How do I know? Because there's an H in the front. Our base is sodium hydroxide because there's an OH. What do we produce? Action is always, you're basically canceling out the power of the acid with the power of the base, and we make water. If we look for our ionic equation, we can see that we're breaking apart the aqueous, breaking apart the aqueous, breaking apart the aqueous, but the liquid is staying together. So in a precipitation reaction, we left the solid alone. The solid stays stuck together. Here, water as a liquid is going to stay stuck together as well. So once again, we can go through and cancel out things that are similar on either side of our equation. And we see then that what's really going on is the acid, H+, reacts with the OH- base to produce water. Our spectator ions in this particular solution would be Na+ and Cl-. So in our net ionic equation, we're always only just showing the things that are participating in the reaction. Another example of an acid-base reaction are ones that produce a gas. So if we've all made a homemade science fair project with the volcano and we mix vinegar with baking soda, this is an acid-base reaction. So you can mix sodium bicarbonate with any type of acid and you're going to produce CO2 as a gas, along with water. Some other compounds that we can mix with acids are sulfites and bisulfites, which form SO2 as a gas. This does not smell pleasant. We can take sulfides and mix them with acids to form H2S as a gas. Once again, not a pleasant smell. And then we can take the ammonium ion, which is NH4+, and react it with a base to form ammonia, which ammonia really doesn't smell very good either. Carbon dioxide has no odor whatsoever. So acid-base reaction going to produce a salt and water, and they can also sometimes produce gases. The last reaction that we're going to study, type of reaction, is oxidation-reduction. And these reactions are responsible for many types of chemical change. These happen in your body. It's a transfer of electrons. So how are we transferring those? Well, the substance that is going to be oxidized is giving up its electrons. For example, sodium. Typically, metals want to give up their electrons. Then somebody has to accept the electrons, which would be the reduced species, right? The thing that's undergoing reduction. So nonmetals like to take electrons to become more stable. So then what we can do is say, okay, if we react sodium with chlorine, what are we going to get? Sodium chloride. A way to remember the difference between oxidation and reduction is to say, Leo the lion goes grr. So Leo, L-E-O, stands for lose electrons, oxidize. Grr is G-E-R, gain electrons, reduce. And you cannot have one without the other. So if something is oxidized, at the same time, something else has to be reduced. The electrons come from somewhere and they go to somewhere else. So what are some applications of oxidation and reduction that we might see in our everyday life? Well, corrosion. We all know that things rust, and especially up here in Michigan with all the salt on the road during the winter gets on our cars. We need to wash it off so that we don't end up rusting out our cars. So iron plus oxygen forms iron 3 oxide, rust. All combustion reactions are going to be redox reactions, and redox is just a shorthand abbreviation for oxidation reduction. So combustion means that we're burning something in the presence of oxygen. This could be metals, it could be non-metals, it could also be types of gas. So our engines in our cars are combustion engines, and we're burning octane as a fuel, and you have to have the oxygen reacting with it, and then we're going to produce carbon dioxide and water, which is why we talk about when we're burning hydrocarbons, when we're burning fuels, all this CO2 that we're putting out into the atmosphere. Carbon dioxide likes to, it's a heat sink, which means it's going to keep things warm. And that's why we've talked, or people talk about how all these fossil fuels are increasing the temperature of the planet, because this likes to just trap the heat. Got to plant more trees. And then another example is bleaching. So using sodium hypochlorite, if you bleach something, we know that it either changes colors or it becomes whiter, but once you do this process, you can't unbleach something. Process, typically oxygen is going to be produced. So some other types of redox reactions are what we call single displacement or single replacement reactions instead of double displacement. So in single displacement, it means only one thing gets to switch a partner. So we start with something alone, something together, and now we end up with a different pair together, and then somebody else is all alone. So some examples of this would be hydrogen displacement. The strontium has kicked out a hydrogen to form hydrogen gas, and then form strontium hydroxide. Down here, we can see metal displacement, which means the magnesium replaced the titanium and formed a new chloride compound. Another example would be halogen displacement, which means that bromine was replaced by chlorine. And not all halogens can replace other ones. Everybody has their own power to either replace something or it doesn't. Some other types of redox reactions are what we call combination or synthesis reactions. So we start with two things that are alone and we form something new. So aluminum, a metal, reacts with bromine, a nonmetal, to form which says, I'm going to take something that's together and now break it apart into pieces. So if I start with potassium chlorate, and apply some heat, I can break that down into potassium chloride and oxygen. Now, not every single combination reaction or decomposition reaction is going to be a redox, but oftentimes they are. However, synthesis or combination still is just looking at two things coming together to become one, and decomposition will always be the reactant breaking down into two or more things as products. As we saw in a previous slide, that all combustion reactions are redox. So that means anytime you see oxygen as a reactant, it is considered to be combustion. So here we have the nonmetal sulfur reacting with sulfur reacting with oxygen to form sulfur dioxide. We can also take metals and react them with oxygen. And here we're burning a magnesium turning to form our magnesium oxide. So other types of reactions, and I mentioned this earlier, double displacement reactions are never redox. And the reason for this is that all of the substances that are in a double displacement reaction are not going to be changing the number of electrons that they begin with, and it happens with redox. We either give electrons away or we accept electrons. So here, everybody keeps their same amount of electrons. It's just that they're going to bond with something new. So double displacement is each partner switches. So the metal becomes with the other nonmetal here, and the metal here becomes with the other nonmetal here. So we always have to have electrolytes that are going to be involved in this reactions because they have to be able to exist in their ionic form so that they can switch partners. We studied these at the beginning of this lecture by looking at precipitation, gas production, which is where we end up with a gas because we've reacted an acid and a base, or neutralization reaction. So these reactions are different from each other in the fact that precipitation forms a solid, gas forms a gas, and neutralization is going to form a liquid. So solid, gas, liquid, these are all double displacement or double replacement reactions.